Meystre at the moment here. Okay. What I would like to start off with is to remind all of you on one of the reasons why we're actually here at the moment, which is the reason why this whole field, or one of the reasons why this whole field actually really emerged during the last year so quickly, which is the availability of high-quality micromechanical systems. And just to demonstrate you one, oops, so this doesn't work now. Wait. Try that one. Okay. There you go. So the availability of high-quality micromechanical systems certainly has boosted this whole field of optomechanics, electromechanics, and so on. And I would just like to give you one example about what we are right now actually capable of with these micromechanical systems. So you all know this seminal experiments by Nichols and Hull in Dartmouth College and Lebedev, Moscow State, so 1901, the first unambiguous demonstration of radiation pressure. That was really a very heroic experiment being performed in this light mill way, this container that actually was, at that time, this was the ultimate world record for vacuum levels that could be achieved, and that's why they actually were able to see those radiation pressure effects. And what they did actually was they had this torsional resonator with a mass of some hundreds of milligrams. They were shining strong light on that and were actually measuring the deflection of this torsional oscillator. And you see that the scales here on a centimeter size. So if we now go to this domain of high-quality micromechanics, we can also fabricate micromechanical systems, mechanical systems that are of centimeter size. However, with a mass that is much smaller. So we have now masses on the order of 100 nanograms. And we have spring constants that are amazingly small. So this is this is a typical set of resonators that we can fabricate right now, where the spring constant is essentially below 10 to the minus 3 Newton per meter, which means if you now have a light source, like a laser pointer with a couple of milliwatts only that shines on this micromechanical structure, you already start to deflect it statically by some hundreds of nanometers. Okay. Now, if you, and this is actually just under ambient conditions, so that's a tabletop experiment. If you then start to modulate your amplitude that you drive it with the mechanical frequency, you get an enhancement by the mechanical Q factor. The Q factor at ambient pressure can be made factor of 100 or so. So you're already almost on the micrometer level of deflection of the system just on a tabletop experiment. And then you take another laser beam, you go away a distance of 10 meters, and you can start to actually deflect a laser beam just on a tabletop experiment with a laser pointer shining on it. So that is sort of, this whole idea actually emerged over dinner with Florian Marquardt a couple of years ago, where he actually said, I want to have an experiment that I can show in my talks that I can actually handle as a theorist. So. So that's why we thought, well, we should do something like that. And it's really nice to hear. Here you can see the reflectivity response of the sample. And if you just scan the wavelength of the laser that is actually reflected there, you see that the displacement nicely follows the reflectivity curve, which is a nice demonstration. This is really a radiation pressure effect. I just put that up to show you that this is, I think, really the power of high-quality micromechanical systems that we have today that are so that are subject to really tiny radiation pressure effects already under ambient conditions. Now, of course, we all know if you start adding a cavity, then many more fascinating things start to happen. First of all, you will have just a static displacement, and if your static displacement overcomes your cavity line width, then you start to see optical bistability. And this has already been mentioned. This has been demonstrated for the first time in a very heroic experiment in Munich and by Dorsel, Pierre, and Mavalvala. So more or less, there are two other effects that happen that were sort of non-accessible at that time, back in the 80s. You also get an intensity-dependent phase shift of your light, which is quite clear. So the more you displace your mechanical system, the reflected light is phase shifted, and that essentially means you got an intensity-dependent phase shift, which is essentially an optical nonlinearity. So it's like a Kerr medium type of interaction, and that's why in the 90s there were a lot of quantum optics proposals how to use such optomechanical cavities actually instead of nonlinear crystals inside the lab to do quantum optics with light. But what you also get is, of course, you get retarded forces due to the radiation pressure interaction onto the mechanical system, which means that you also modify the mechanical susceptibility. And what you have at hand now is suddenly an interaction that couples your intracavity field to your mechanical system. This would be the full interaction. And it has been pointed out by Peter already, if you just take a regular Fabry-Perot cavity and one of those oscillators that I just showed you, with the numbers that we have, frequencies on the order of hundreds of kilohertz or up to megahertz, the mass is on the order of hundreds of nanograms, and you calculate actually your coupling rate here, single photon frequency shift. So the displacement in your cavity frequency when you shift the mechanical oscillator by 1 ground state extension, then it turns out that this coupling rate is on the order of a few hundreds of hertz. So that's relatively small still compared to your cavity bandwidth that is some megahertz that you have to compare it with in terms of your frequency shift. So what you can do is you can drive your optomechanical system. What happens is the interaction linearizes. You get a steady state cavity field, and then you get your fluctuations on top. And you get something which is sort of right now state of the art of quantum optomechanics. On the one hand, if you drive your cavity resonance, here's your pump frequency and your cavity resonance, then you have this XX coupling between the amplitude quadrature of the light field and your mechanical amplitude quadrature, which essentially resembles a quantum non-demolition interaction for the amplitude quadrature of light. What you can do, however, now is to detune your cavity with respect to your pump field. If you detune it, so if your pump is detuned on the red side, what you effectively get is a beam splitter interaction between the optical field excitations in the cavity mechanical mode. The way to understand that is that sort of the only way to create now photons inside the cavity is actually by taking energy from the mechanical system. And what you get is a coherent energy exchange, which is a beam splitter interaction. What you can also do is, of course, you can actually put your cavity on the other side of your pump, so such that the pump is blue detuned. And now you can see that the only way you pump photons into the systems is by also exciting the mechanics. And what you get now is a mutual excitations of optical and mechanical modes. And this is actually known in quantum optics as a two-mode squeezing interaction. So what you have now, by simply detuning your cavity, and this is of course all in the ideal case that you are in the resolved sideband regime and that the rotating wave approximation is valid, so that your coupling is still weak, so your G0 alpha is still weak compared to the mechanical frequency. So if you are in this ideal regime, what you have at hand now is, by simply detuning your cavity resonance with respect to your pump beam, you actually have a full quantum optics toolbox now, with which you can play and with which you can control your mechanical quantum state by means of your optical quantum states. Or on the other hand, you can of course also just control now your optical states by means of your optomechanical state. Of course, so the sort of analogy that I would like to draw here is really the classical case of two-mode quantum optics. So this is the situation that people in quantum optics have been looking at for tens of years now, that you have two optical modes. You have a nonlinear medium. When you pump that, you get interactions that are essentially, well, in most cases of this of the parametric downconversion type. But essentially, what this nonlinear interaction between the two optical modes does is to correlate your quadratures of your two modes. And what we do now in this case here is we simply replace one optical mode by a mechanical mode, and our interaction here is essentially our optomechanical cavity. So this is the way I would like to think about that. And then, of course, you can ask, well, so we know that all those interactions can be actually used to do state transfer, to in that case to generate quantum entanglement between modes. So what is required for that? Well, what is essential, of course, that typically in two-mode quantum optics, these are two optical modes, and you operate that at room temperature and so on, and they're essentially in their ground state. So you have pure states that you start off with, and that's something you want to realize, and that's why minimum entropy mechanical states are sort of a requirement to really play the game here of quantum-optomechanics. And what you also would like to have, because here you have finite cavity decay and so on, so you want to operate in a regime where you exchange here that takes place really can occur in a coherent manner, so you better try to operate in a regime where you are at time scales beyond your decoherence rate, so you want to operate in the strong coupling regime. Now, I don't want to go now into all the details, because there will be also many talks on cooling and so on. But the main message is, if you look in the into the beam split interaction, so the first one that was up there, this interaction is a coherent exchange between optical and mechanical excitations. So that means you create photons inside the cavity on expanse of a mechanical excitations. Your cavity decays as a finite lifetime, so photons that leak out of the cavity will carry away energy of your mechanical motion. This you can actually also explain in a picture of Raman scattering, and also in a picture of Seipen-resolved cooling of ions. So Peter has already mentioned that, and there are several theory papers also on that. And you can see that there was, with this availability of the micromechanical system since 2006, there was a series of back-to-back publications. So within like a time scale of 2 years, there were many groups that demonstrated this radiation pressure cooling effect. And I think it's fair to say in experimental physics, such a time scale essentially counts as more or less back-to-back. So the effective cooling rate that you get is then, again, still in the regime of the rotating wave approximation and recoupling your G squared over kappa, which is, of course, reminiscent also of atomic cooling. The difference now is here that your final effective mode occupation of your mechanics will, of course, be limited by your decoherence rate to the environment. So you better have your thermal decoherence rate small, which means you better have your temperature small and your mechanical quality factor high. But of course, the ultimate limitation here, you see, is if you operate in a Seipen-resolved regime, so if your cavity line width is small with respect to the mechanical frequency, well below the quantum ground state. So as I said, what you essentially want to do is, in order to reduce your final occupation number further, and in order to achieve a as pure mechanical mode as possible to start off with, then to actually do quantum optomechanics, first thing to do is reduce your temperature. There's a series of experiments that are going on. That is an experiment that we did back in 2009, where we put our whole mechanical system in the cavity into a 4K helium, so into helium-4 optical cryostat, and simply demonstrated the optical cooling. The interesting thing about that experiment was that our final occupation factor was really only limited by the thermal coupling of our mechanical system to the environment. So there were no absorption effects that would actually increase our mechanical occupation, because we had very high quality mirrors with really incredible absorption values below 1 ppm. So here, because of the fact that we weren't limited by any absorption effects, the next reasonable thing and logical step to do is, of course, reduce the temperature further. And this is something that we are working on right now. So as I'm speaking, so to speak, we have developed, together with a company then called Very Cold, a new type of dilution refrigerator, where we have complete optical access via windows to a 25 millikelvin base temperature reservoir. So this is already in operation. So we actually have here windows with quite some large aperture, and we can directly access our sample stage at 25 millikelvin. This is a closed cycle dilution refrigerator. We have achieved now stable operation of an optomechanical cavity with finesse beyond 10,000 with everything on. So this thing is really shaking if you have ever seen such a closed cycle dilution refrigerator. So at the base of this working principle is the Joule-Thomson effect. So compression, expansion of helium-4 gas, and this is really shaking quite nicely. I think it's worthwhile for the experimentalists in the audience to point out this is a extremely interesting sample suspension that we built here. So this was the idea of Jan Töne to you see that here the sample chamber is actually connected to two rods solidly, and these rods here are connected boldly, solidly to the optical table. So this is rigidly mounted to the optical table, and the dilution refrigerator is actually floating around that. Right? So it's in a way levitating. So it's a levitating dilution refrigerator experiment. So we have that mounted then on the, we hang that down from the wall, and the only connection to our sample chamber is here really via copper brads that thermalize. Right? So you can imagine your experiment is still fixed on the optical table, and your whole cooling instruments are floating around there. Yeah, so it's working quite nicely, and as I said, as we are speaking, experiments are currently underway. I wanted to bring some data already, but you know how it goes. You cool down, you start seeing something, your piezo breaks, you heat up, and 2 weeks are gone. Yeah, everything is, I would say, nicely working now. Okay. Now, the next thing that I would actually like to ask now is how can we get rid of the cryostat? Because the experience tells us, so we spent quite some time with these low temperature stages, and actually it's amazing that you can, that even a person from quantum optics can now operate such a thing. This wouldn't have been possible 10 years ago, I dare to claim. But now you have these nice devices, but now that you're there and you spent plenty of time to get it working, you have to ask the question, can we do room temperature quantum optomechanics? So what is sort of the requirements to achieve that? And well, if you think about it, there are essentially two conditions, and it's more or less what Peter already had in his talk. I just write it down a different way. So if you want to achieve a mechanical occupation much smaller than 1, what you essentially want, and this is all in the, again, recoupling and rotating wave approximation, is that your thermal decoherence rate is much smaller than your cooling rate, which essentially boils down to the requirement that a parameter that you could call cooperativity is much larger than your bath temperature. So this is your G square over kappa gamma, so the two relevant decoherence timescales, and in atomic physics, something like that is called typical cooperativity. If you put down the numbers for, let's say, a oscillator at a megahertz or so, or 6 megahertz, a temperature of 300 Kelvin, your bath temperature is of the order of 10 to the 6. So you need quite a large cooperativity to do that in principle, starting from room temperature. Then, of course, there's another condition that you have to fulfill, namely that your thermal decoherence, that your system actually doesn't decohere on the timescale of 1 oscillation. You want to have some coherent oscillations, and well, if you spell that out, you actually get a nice Q times F, so a nice condition on your Q times F product, which typically in nanomechanics and micromechanics is sort of the benchmark number for the performance of your system. And you see that your Q times F product has to be on the much larger than, so this is the number here, and if you spell it out, on the order of 10 to the 10 times the temperature. So, which means if you want to operate at 300 Kelvin, your QF product needs to be much larger than 10 to the 12. the frequency. It's just the frequency. So omega is 2 pi f. So it's just a mechanical frequency. So QF is just a technical term, so I introduced that instead of Q omega. One additional comment here, because we had a breakfast discussion this morning, so I just want to mention it. Beware the phase noise. So these are, of course, the fundamental limits, if you think about it, but then there are some other fundamental practical limits that Tobias will, I think, be talking about in his talk. So I just say that now, that this is not the whole story, of course, once you want to do the experiment. Okay, so question now. So we need a large QF product so that we can increase so that the first condition that we can fulfill that, okay, well, you just have to crank up your power. But what about QF? Well, so we are working along several directions, how to actually improve our mechanics. And there would be many things to say here, but now for the sake of this talk, I would like to say that so with regular mechanical devices, so typically where your R is on the order of 10 to the 10 to the 11, maybe 10 to the 12. So it's sort of, this is what you get for optomechanical systems, and I'm sure that now within this conference we will get some additional numbers. But so 10 to the 12, I think, is a nice number that you can more or less easily get nowadays in your experiments and in your microfabrication. Maybe just as a side remark, and I will switch topic immediately again, we have started to actually work with micromechanical systems that are completely single crystalline, but still resemble a Bragg mirror. So here you have then many layers of varying contrast of index of refraction. So light is actually reflected here perfectly, so it's a perfect mirror. You can microfabricate that, and it's grown out of single crystalline material. So it's epitaxially grown. The advantage here is that you minimize the internal defects in your material, and your Q factor gets higher. And by the way, since it's highly reflecting, if you make coatings out of that, your phase noise gets drastically reduced. So these are two advantages, and so brackets closed. Okay, so as I said, for room temperature quantum optomechanics, you want to boost your QF even more. And I just would like to point out there are a couple of ideas. Again, I'm sort of now borrowing from Peter's talk. Recently, there were a couple of proposals by Peter's group together with Jeff and by Ignacio Sirach's group that to optically levitate a system, a dielectric object. And what you achieve by that is, of course, you isolate it from any supports to your solid state system, and that should actually allow you to achieve very high mechanical quality factors. And I think both Oriol and Mark will be talking about that. And what you also have, of course, if you put that in a cavity, you again have a mechanical oscillator coupled to a cavity field, and you can do quantum optomechanics with that. So you could actually now use the cavity field to cool it to the ground state and so on. So there have been a couple of proposals how to then generate actually how to realize single photon quantum state transfer, also utilize quantum state teleportation and so on. And one thing that has not been published yet, but that you will see in Oriol's talk, I think, is how you can actually use that to generate really macroscopic quantum superpositions. And the main idea is essentially you prepare the ground state, and then you just switch everything off, and now your ground state wave function just expands. And then once you have a macroscopic wave function, you can start manipulating that, and I won't spoil Oriol's talk. And so this I mean with free fall. Okay. Another thing that is worth mentioning is this is a paper that came out by Jeff and Oscar recently. They sort of combine now this levitation approach with a suspended object. And here the main idea is you have a suspended object that already has some QF product, and then you trap it optically. So you just put it in your cavity. What you essentially do is you have an additional optical spring that shifts your resonance frequency, but your dissipation mechanisms remain unchanged, essentially unchanged. So that means that you shift your frequency and your Q times F increases accordingly. That's something that is also being done, by the way, by the LIGO guys, because they have to stabilize their mechanical, their large mirror at larger frequencies, because their suspension works at 10 hertz or so, and they have to shift it slightly, and so that's something that has been demonstrated also there. Now, the nice thing about this membrane here is they estimate that a Q times F of the order of 10 to the 18 should be possible. And that would, of course, be fantastic if that is true. So, and as I understand, it's really something they would like to try out, and I think this is a extremely exciting idea, big idea for a new direction, namely room temperature quantum optomechanics. Okay. Now, I've talked all the time about the first part of the possible quantum optomechanical interaction, namely retune your laser beam and try to get some quanta out of your system. Well, what about the other side? The other side, I told you, essentially resembles a two-mode squeezing interaction or a downconversion interaction. Well, when you come from quantum optics, downconversion is an extremely nice thing. You take your nonlinear crystal that does downconversion, you pump it, and you generate signal and idler modes that are, if you pump it strong enough, entangled. So you can actually achieve EPR-type entanglement between the quadratures of light of two continuous rebel beams by using this parametric downconversion interaction. There was an experiment that essentially was done by Kimball and Peng back in the 90s, and they demonstrated this EPR entanglement exactly in that way. So that actually I borrowed this picture directly from Chad's paper. So just to remind you, this was the idea, the analog for quantum optomechanics. So it's the same. Now you replace one optical mode by mechanical mode, but by choosing a proper detuning, you can have also the same downconversion interaction. So shouldn't we be able then to see entanglement between the mechanical mode and the optical mode? That's the question. Or at least see some signature of this two-mode squeezing. So how does an experiment look like? If you do that, well, so here's your optomechanical cavity. So you want to have two things. First of all, you want to so you pump your system, and you want to correlate the quadratures of the mechanics and the optics eventually. So you first need a readout of your mechanical system, and this is something that we know how to do. We have a very weak laser beam that is resonant with our cavity and that couples to our mechanical system via the phase quadrature of this very weak light. Okay, so here's a very weak probe beam that reads out the mechanical position quadrature. We have a homodyne measurement here, and if you demodulate the whole thing, then with a electronically with a signal that is of a resonance frequency, you can actually get both quadratures, the amplitude and the phase quadrature of your mechanical system. So this is what's done here. So here we have a readout of the generalized mechanical quadrature. The other thing that you want to do is you want to have a readout of your cavity field. Well, what you do there is, so here you have your strong pump field, and so this is the strong one. And what you do is now you have a second independent homodyne setup that actually does homodyning of your sideband of your reflected light here, which is a direct, which gives you direct information on your cavity field. Okay, so here we have sideband homodyning of our pump field, which provides you with the generalized quadrature of your cavity field, and here we have the homodyning of our mechanics. And what we want now is to calculate the correlation function between the light and the mechanics when we switch on the interaction. Okay? Okay. So now, problem is, as most of you doing experiments know, if you just switch on this interaction, all hell breaks loose. Okay? Your system essentially starts to become unstable and so on. Plus, we are still at room temperature. Okay? So what we ideally want is we want to cool our mechanical system and then switch on the optomechanical downconversion to generate the entanglement, because we want to start out with a pure mechanical state. Well, so here's the trick. The trick is pump your system on the red side. So you basically do your laser cooling, but now keep cranking up the power. Okay? What we said before is that all our analysis assumes the validity of the rotating wave approximation. But what happens if you enter a regime where the rotating wave approximation breaks down? Well, what happens then is that in addition to your co-rotating terms that you get from the rotating wave approximation, the counter-rotating terms, which are actually, in that case, the two-mode squeezing term, starts to kick in. Okay? So sort of you now have this serves a dual purpose now, driving it at the red side. First of all, you start cooling your system, but if you drive it hard enough, the breakdown of the rotating wave approximation will generate additional interaction of the two-mode squeezing type. So you get, for free, a cooled system, a purified system, plus your nonlinear interaction that should generate entanglement. So that's the idea. So we started to work on that, and here you see some experimental data. When we drive extremely weakly, so here our coupling is much more smaller than the mechanical frequency, you see here as a plot the mechanical quadratures, so actually that's the generalized mechanical quadrature, so that the phase of the mechanical quadrature versus the phase of the optical quadrature, and you see a nice symmetry here, straight line. And that makes sense because if you couple weakly, the only interaction that you have is the beam splitter interaction, which means that you map perfectly your quadrature of your mechanical system onto the optical system. Okay? So that means that once you have one pair of quadratures fixed, and you change now the phase of one, it has to follow in a straight line under 45 degree the optical quadrature. Okay, so that makes sense. What happens now if you start to drive it hard? The rotating wave approximation will start to break down, and you will start to break up actually your symmetry. You will start to create correlation. And what you can do now is you can start. Oh, definitely. Yeah, that's the point. Right? I mean, well, so if you would have a perfectly entangled state, okay. So let's say you generate a perfectly entangled state, two-mode squeezed between mechanics and optics, and you would now just look at the temperature of your mechanics. That's equivalent to just tracing out the optics. Well, so it's a thermal state again. Right? So if you just look at the mechanics, it actually has to warm up. Right? It's sort of a necessary criterion. Yeah. But definitely, but by no means sufficient. That would be nice. So if you now start to analyze the data and compute the correlation functions that I just showed you, then so this is now the correlation function between the pairs of quadratures. So you have a correlation function between the generalized optical and generalized mechanical quadrature, but you keep your phase difference fixed now and rotate it jointly, which means that when you start off with an XX correlation here, and you start to rotate now jointly the two phases, you will go to a PP correlation. So amplitude position correlation will actually go into after some point, so after half a period, into momentum phase correlation, and then we'll go back when you continue to rotate the phase to position. And in the case that you don't have any parametric downconversion interaction, you would just expect that both your position quadrature is correlated and the momentum phase quadrature is correlated. But if you start to crank up the interaction from two-mode quantum optics, what happens is actually that your position quadrature is still correlated, but your momentum, or in that case momentum phase quadrature, starts to become anti-correlated. And this is actually what you see here. You crank up the power, and a correlation in one pairs of quadratures will start to go more and more into the direction of anti-correlations in the other pairs of quadratures, which is a signature for this parametric downconversion interaction. So this zero here that goes into anti-correlations is, of course, a zero that is given by thermal noise. So right now, what we do, this is all purely classical, and what we see here is we start to see a squashing below the thermal noise of our system. Now, it would be nice, of course, to put that now into the cryostat and then start operating. Now, the question to ask is now, of course, there are a couple of questions that come up here. First of all, well, you told us now that what you do is you measure you want to measure entanglement between optics and mechanics, but what you do essentially is just correlate to optical fields. So how valid is that? So first of all, how would we demonstrate entanglement? Well, we would compute actually those correlation functions, and there's a very nice general criterion that you find here in this 2000 paper by Ignacio and people. So the question is, if we would demonstrate entanglement between the two optical modes that I showed you here, is that sufficient to actually demonstrate optomechanical entanglement? And this is not a trivial question. There's a beautiful paper also by Ignacio, and I still find it amazing that Ignacio had a PhD student who was called Qubit. I still find this very, very beautiful. So so in this paper, actually, if you read that, you will see that this question that I pose here is a non-trivial question, okay? Because there can be situations where actually you have three parties, and where you can transfer entanglement between two parties to between A and B to A and C without ever having actually B and C being entangled. So this is that's why this question is legitimate. But it turns out, so we have done such an analysis already some time ago, and for this specific type of interaction that we have, in most cases, if you choose your parameters right, you will always be in a situation where entanglement between the two optical modes is actually necessary and sufficient for having entanglement between optics and mechanics. And you can actually even generate a situation where you have genuine tripartite entanglement between the three systems. Of course, what you can also do, this would be a next stage, you could decouple that by having pulse sequences, right? So you have one pulse that entangles, and then causally disconnected a second pulse that reads out. And that would be the solid proof, I would say. But that's another story, because pulsing is also not so trivial. The second thing, and I think this will be more or less my closing remark, is the question, well, so what about optomechanics in a non-Markov environment? So right now, the paradigm, more or less, if you look at most of the papers, is that the Brownian motion of a micromechanical system, a nanomechanical system, is Markovian. That's sort of the main assumption. But what that more or less means is that your spectral density of your heat bath, in the case that it's weakly coupled and at high temperatures, has this form as proportional to the frequency. What that means is that your mechanical noise spectrum, so when you just look at your frequency response of just a Brownian-driven mechanical system, looks like that. And this is actually what we always use to fit our data if we have nice mechanical curves like that. And so this is the sort of paradigm way to do it. There has recently been a nice paper by Florian Marquardt and Clemens Hammerer, together with Max Ludwig, on the question, well, maybe can non-Markovian environment be sort of effectful, let's say, to entanglement? So both in the positive and the negative way. And the answer in that paper is yes. So it might be actually quite relevant to know the spectral density of your bath that you have. And if you then look further in the literature, for example, in Ignacio Wilson-Ray's paper, he actually shows quite nicely that even the mode geometry, so the way how your mechanical system actually looks like and is connected to your environment, can actually result in quite some non-Markovian environments. So I think in your case you can only generate sub-ohmian, but that's what I. Okay. So okay. I took that out of your paper. So okay. Anyway, point is, what does that mean? Well, you can actually now assume that your spectral density is something like omega to the k, and then if your k is not equal to 1, it's non-Markovian. So if it's smaller 1, it's sub-ohmian. If it's larger 1, it's super-ohmian, and so on. Question is there a way to directly measure the properties of the spectral bath? In particular, can you measure the local gradient of your spectral bath density, okay? And basically extract this exponent k, which can be of relevance for your dynamics if you want to generate entanglement. Well, to make a long story short, if you generalize your whole treatment of your mechanical system and put in a general form of your heat bath, your thermal noise spectrum looks a little bit different, and you see that suddenly this specific form of I of omega occurs. And then you have to do some, let's say, non-trivial analysis so of your spectra. Bootstrapping is actually the buzzword here that we use to do that. And what you get is a distribution of your possible K values that best fit your thermal noise spectrum. And it turns out if you do that with several data sets, then what you get is a clear shift away from the Markovian behavior. And that is just a typical micromechanical resonator just coupled to a bath. So there's no effect of the optomechanical coupling. This is just the environment of the mechanical system in the sort of unperturbed state. Okay? Good. Okay. So I'm running out of time, so I would say I essentially stop here. What I just wanted to say in the last remaining slides is essentially something that was also already mentioned by Peter, that once you really look into the single photon regime, so in the strongly coupled regime, you get so. First of all, if you just look in a strongly driven regime, what you get, of course, is normal mode splitting in your optomechanical system. So you're, in a sense, the cavity decays of your photons in the cavity can only occur between now dressed states of your optomechanical systems, and you get this normal mode splitting. But of course, it's an extremely interesting question to ask, well, what about the single photon regime? Because in a single photon regime, you actually don't have this whole ladder structure. You have strong nonlinearities. There's the possibility of vacuum-Rabi splitting. So wouldn't that be a scenario where you can really do quantum optics with very strong nonlinearities? And there will be, oh, this was missing. I want to say, see talk by Peter Rabel, right? So he will talk about single photon regime, and I think also there's another talk from the Yale group on single photon regime. So I think it's an interesting question, and I would like to point out that actually there is a chance of entering such a regime. In particular, if you look at those beautiful new approaches, I think this also goes on the big ideas of actually near-field optical effects in waveguides, in optomechanical crystals, and so on. So the coupling rates in those systems, in particular in these optomechanical crystals, is so large that I think this might be a possibility to look into those single photon coupling. Okay, let me wrap up. I think there are a couple, I would say there are a couple of big ideas out there. They touch more or less those three fields. What I didn't really talk much about is the foundational aspect, which I personally find one of the most attractive ones of the field, because I think it's an outstanding question to address. How large can we actually make the objects? How massive can we make the objects? How macroscopic can we make the superposition by means of optomechanics? And I think personally that optomechanics really has given us a very, very powerful new tool to explore the regime of macroscopic quantum physics. And that is something that really needs to be addressed. I mean, if you want to push it, you could even ask the question from at one point, will we be able to actually create by means of this optomechanics quantum states of massive systems that are large enough that they are actually subject to gravitational fields, and that you could then experimentally really couple quantum states to some gravitating object. But as I said, so this is just pushing it, but I think this is a direction worthwhile thinking about. Quantum information, Peter has beautifully talked about, and there's another direction that we also really didn't go into, namely the possibility to utilize those non-classical mechanical states, for example, highly squeezed in positioned space mechanical states, then for improving measurement sensitivities even beyond the incredible resolutions that we have already today with those micro-nanomechanical systems. Okay, so this is my opportunity to really say thank you to all my collaborators and my team. So most of the work that you have seen here has actually been performed by Simon Gröblacher, who has actually finished now and will join the Caltech team very soon. Garrett Cole, who is responsible for all the micromechanics. Alexei Chubarov has worked with Jens Eisert on those non-Markovian business. Sebastian Hofer and Clemens Hammerer are the ones who do the theory support for our parametric downconversion experiments and also our strong coupling regime. Then, of course, Clemens, I want to actually say thank you, and also with Oriol, who will talk about those macroscopic superpositions. We are talking a lot, and with Oscar and with Ignacio Wilson-Ray, we are currently in very strong collaboration. Okay, with that, I would like to thank you. Mm-hmm. Well, yeah, so that's actually something that we also have been discussing now the last 2 days, right? We haven't yet, actually, we don't have an answer yet, because one possible response, and so basically, so this is a comment that Peter Rabel made, is that typically what is relevant is only the behavior at small frequencies, where actually your spectral density starts to diverge if you are sub-ohmian. And this is then where you really would expect large effects in dephasing and so on. But on the other hand, talking to Florian yesterday night during nice Mexican dinner, turned out that in his paper, the spectral the slope, so the exact shape of the spectral density is of relevance for these calculations that he did. The slope at the resonance, yes, exactly. Right? So it can have an effect. I mean, it's not clear yet how strong you really have to be. So maybe it only makes an effect when you are sub-ohmian with an exponent of, I don't know, k of 7 or 8. I have no idea. That's now something we simply need to think about. But obviously there are, if you put in the numbers, then the local slope at the mechanical resonance seems to play a role. So let me reinterpret Dan's question. I thought he was saying that essentially it's surprising that the local slope would matter for. Okay, good. So was I. Okay. And now I would actually. This is also the reason why I put that up, because this is work in progress, and I would like to understand. Right now, I don't have an intuitive understanding why just such a narrow band should be of relevance, and that's. Yeah. So I would be very happy to discuss exactly this question. I don't have a good answer to that yet. And I don't have an intuition for that right now. Okay. You mean, given now just this approach? Now, in that case, you would also need to have a drive that is sufficiently strong to be in the order of breaking the rotating wave approximation. So that would be actually ground states cooling under the condition of strong coupling, which is something that I think Ignacio and Tobias have essentially worked out. So it's a little bit modified condition, but then it's the same. Yeah, similar. Mm-hmm. decreasing case. Oh, you mean if you would just look at your mechanical noise spectrum, how would that look like? Actually, I would expect. If you just look at the plots, just of the data that we took, right? So that is still, without any detailed analysis, still is unchanged. Okay. In a way, I think that's what I would expect with the same argument that on Pierre's question, that if you just look at the isolated subsystem, it won't look different than just a thermal state. So you would only, I think you would only see it as a sort of effective increased temperature. So, because you, yeah. That's a good question, actually. So whether this might be an additional feature that would come in. I don't know. My expectation would be that the non-Markovian case would more or less just change the parameters that you require to go into the squeeze. Right. Right. It's the tube. That is the main point, that your field of view at the sample stage is first of all small, and secondly that the thermal conductance over this large tube is actually such that you really can have a gradient from 300K down to 25 milli-K. I mean, that was actually the main difference in the design. So the tubes here are not there for fun. This is the minimum length actually that you require to exactly do the decoupling from room temperature down to the 25 millikelvin. If you would make that smaller, so if you, I mean, there are other dilution refrigerator systems that don't have the tubes, but just small windows, right? And they typically, when you have comparable cooling powers than we have, like 200 milliwatts at 200 microwatts at 100 millikelvin, they would actually achieve base temperatures of 100, 200 millikelvin. Okay, so and only the fact that you go out now, and yes, it's actually it's a glass fiber, so it's carbonated glass fiber. Because it had to be rigid enough to not actually wobble, because that's our solid architecture for the cavity, but the thermal conductance had to be good enough to actually withstand the gradient. And then it's like I think this size per leg that you need, so around a meter.
I'll catch you before everyone else does. Yeah. So when you talk about breakdown of rotating wave, right? perfect optical detection, no losses or anything like this. Will I really see ideally like pure two? I'm going to be in a pure state.
More or less. I mean, this is this. You do have some general path entanglement.
Okay.
So that will degrade your
Okay.
But that really strongly depends on the sequence.
Okay.
So you can certainly find a frame division.
And I don't have to do anything where I would say weekly measure and give up for poor efficiency in the measurements where I only use sort of, it's really okay. Okay. Yeah, right.
So you still get some noise when you go more.
In,
Get some extra noise that you have to take.
okay, so okay.
So that will actually add to your non-trivial.
Okay. Essentially, what it means is roughly that if I sort of pay attention to modes outside of the cavity, my measurement includes modes which somehow haven't been processed by the cavity. It's like I would say there's sort of Fourier frequencies and Fourier domains. I should let Eric talk to you with
I think that's that must be fair to say.
okay. All right. I hope I get a chance to talk to you a little more this week.
I'm leaving Tuesday night.
Tuesday night. Okay.
That's my only boundary condition. Other than that, I'm here to learn and talk.
Okay, absolutely. Maybe John and I will come and pick your brain a little bit.
Oh, please.
Okay. Very good.
So tell me again about this tube.
Yeah.
You said it was optical fibers?
Well, you know, it's the I don't know how it's called. This is carbonated optical fiber. So it's an how is it called? Don't you have such an expression? Carbon fiber?
Yeah, carbon fiber.
Yeah, exactly. It's carbon fiber. So it's very solid material, no?
Yeah.
Carbon fiber.
Yeah. Okay. I mean,
the material that you make the boats out of. How is it
yes,
called?
fiberglass.
Fiberglass. Yeah, exactly. Fiberglass. Sorry.
Yeah.
It's fiberglass, but there's some carbon inside, no?
Yeah.
It's carbonated
Well,
fiberglass.
it has epoxy.
Yeah, exactly. Yeah. It's that essentially. Right? So how do you call it? Give me the right.
It doesn't have the fiberglass in it. It doesn't have the woven cloth. It just has the glue, the fiberglass. I mean, it has the epoxy.
Right. Exactly. How is it called? So it's. How do you call the material? So
we call the whole prepared material fiberglass.
Okay.
Yeah. I mean, make a boat out of it.
Good.
Right.
So okay.
Yeah.
So it's made out of fiberglass.
But it's completely transparent.
It's just a tube. So it's not a.
Oh.
So it's just a tube with a wall size of like maybe half a centimeter. So.
Okay.
Like a few millimeters.
Okay.
Right.
Okay. So you have this fiberglass tube.
Oh, it's like that.
Yes. Okay.
Yes.
This fiberglass tube, and it has windows on the end.
Exactly, and at
both
70K, 4K.
Yes. Yeah.
Mm-hmm.
Oh.
Right.